Hello and welcome back to another installment of LeetCode. We're looking at another medium problem, LeetCode 236, lowest common ancestor of a binary tree. I have attempted this one before, but that's a long time ago. So hopefully I can solve this now without looking at any of the example solutions. And as usual, we're going to do our LeetCode interview practice, which means we're going to really trying to be very vocal about what we do in order to solve it. And yeah, let's do it. So we're given a binary tree and we're supposed to find the lowest common ancestor, the LCA of two given nodes in the tree. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node T that has both P and Q as descendants, where we allow a node to be a descendant, we allow a node to be a descendant of itself. So, okay. And we are given a root node as an input, and we're giving two tree nodes, of which we have to find the lowest common ancestor. But the tree structure is that we only have pointers towards the children, so not to the parent. Okay. That'll make things a little bit more difficult for us. Okay, let's look. What else do we know? Oh, we know that the tree nodes P and Q are not the same node, and that they are guaranteed to exist, and that all node values are unique. So we can actually perform a search by node value. Now, unfortunately, we're not dealing with a binary search tree, just a binary tree, so we cannot use the node value to navigate through the tree from the root. And there are some constraints on the values of the nodes, which was not really interesting for our problem. And the number of nodes in tree is in the range from 2 to some number. But we're going to ignore the upper bound. Otherwise, our runtime and space analysis are going to be O of 1, which is super not interesting. So we're going to pretend like, we could have n nodes in the tree. But the minimum number is 2 because P and Q will exist and they are not the same. Cool. So let's have a look at these examples here now. So here we have a nice tree with root 3, and we are looking to find the lowest common ancestor of root node 5, 5, and 1, which is 3, right? And by the way, low means the first ancestor when we go up, right? So the leaves on the bottom, those are the lowest nodes. The root node is the highest node. Otherwise, if the lowest common ancestor was actually the highest one, we just return root all the time because, every other node is a descendant of root. So that wouldn't make any sense. So the lowest one means the one that has the highest depth and that is still an ancestor of both of those nodes. Second example. So we're looking for the lowest common ancestor of P5 in Q4, so 5 and 4. Well, that's 5, right? Because 4 is a descendant of 5, but not the other way around. So that's why it should return 5. Okay, here we have another example. We have a root node. Wait, how do you read this? Oh yeah, first one is the root, and then comes the left child, right? So now we're looking for their lowest common ancestor. That's of course the root node 1. Right. Okay, cool. And what are we supposed to return? Well, we have to find that node to return. So, so we can see it here in the method signature. We're actually supposed to return a node object and not just the node value. Cool. So I think, I see a linear time and linear space solution where linear time and space mean height of the tree, because we're going to do, we have to wander the path down the tree to find those nodes and then find their common ancestor, the lowest one. So we have to traverse potentially all of those nodes because we have no other way of navigating this tree, right? We can only navigate downwards towards the leaves from P and Q, but we cannot navigate upwards. So we have to start from the root explore all paths to find the node P and to find the node Q. So we have a node search component that's going to be O of n time and O of h space, where h is the height of the space and h is smaller or equal than n. So essentially both is going to be O of n time and O of h space, where n is num nodes in tree and h is height max. Well, height of the tree is the maximum height of the tree, right? From level 0, 1, 2, 3. So this would be a tree of height 3 or 4, depending on whether you count the root node as index 0 or index 1. Well, no, depending on whether you count the nodes on the longest path as the length or the edges on the longest path, right? So 0, 1 edge, 2 edge, 3 edge, or 1 node, 2, 3, 4 nodes. Anyways, I'm rambling. So yes, so now, well, I think we can split the problem up like this. So we need to find the path from the root to P and the path from Q to the root. Once we have those two paths, we can compare them, right? We simply walk them in parallel from the root. And as soon as we see that the path go into different directions, that means we have found the lowest common ancestor. Because once they split paths, we know that they don't have a common ancestor on those paths anymore. So that's what we will do. So we're going to do a little def find node, or get path to node. Path to node. By the way, if you're in an interview and you're giving like camel case or whatever, just mimic that code style. You know, even if it's not PEP 8 compliant or whatever, just mimic the code style. And you can say that as well. You know, makes you look even smarter. I'm not going to follow PEP 8. I'm just going to follow this code convention that I see in here. And I hope that's okay. Easy. So we start with the current node where we are, the target node, and we have to build a path towards that. So path P equals get path to node. And this is also something, you know, sometimes you don't have these functions ready, or you could say, well, I need a function that does X, and then you can just pretend that you already have that function. You know, if you're running short on time, that's a nice technique to use. And because it allows you to still, you know, construct the algorithm to solve the problem, even if you can flesh out all of the detailed implementation. So this can be a time-saving technique, but also a technique to focus on the high-level design of your approach first. So we start at the root, we put in P, and the path will be empty when we start. And now we do the same for the path to Q, right? And in our path to node method, we're just going to return the path at the very end. That's all we do. So, and well, since we're not under time pressure, we can flesh this method out. So we say if not cur, well, that's not going to be part of the path, right? Return none. That means we didn't find the node. If cur.val, well, actually, we can just do this. If cur equals target, because we're giving tree nodes already that exist in the tree, so we can just compare the object references. We don't have to compare them by value. So if current targets, then we're going to return. Actually, if we don't have anything, we just return the empty list. Otherwise, we're going to return a copy of the path. And this is a short way of copying a list with this notation. So that is now the path. Easy. And well, if that's not the case, well, what do? Well, we have to check the right subtree and the left subtree. So if, so we'll say result. Actually, I'm going to rewrite this slightly. If not current, well, if current is a node, otherwise we're going to return result. And now we do this edge case. So if the current is equal to the target, then we're going to say result is that. Yeah. Otherwise, well, we need to go left and right. So we check result equals, and now we do get path to node, query.left, and the path itself. Well, that means we have to path.add append current. And before we exit this method, we have to actually pop that element out of our temporary path. Pop. And this little trick, where we pass an array that we kind of use like a stack, it means we don't have to rebuild or copy the entire path. Whenever we go into the recursion, we're just going to add one more element to the path and then remove it later. So that's a space-saving technique. Otherwise, at every depth of the recursion, you would have to copy what the current path is, and then that degrades to an O of n squared time and solution, right? And space as well, if you hold on, or if you build that out and then go into another recursion. But yeah, so we don't want to do that. So let's see. Otherwise, we do this. If res, well, if not res. So we try to find to get a path to the target node by following the left branch. If we get back something that is not the empty list, that means we've actually found the path, right? So that's perfect. But if we didn't, well, then we have to try the right path as well, right? And it might or might not have something for us. Doesn't matter. We're going to return it at the end. That's how that works. So yes, so let's see. That should be everything we need for the path finding. Now, the two different paths can have a different length, but we know they both start at the root. So now all we need to do, we have to find the lowest common ancestor. And well, we can do this with a little index. Actually, we could do it with a little index if we wanted to. Well, because we now have the nodes in this order where, so to 5, 3, 3, 5 would be in the first path. And then the second path would be 3, 1, right? So here they're the same length. So we could use an index to iterate over them in parallel. In the second case here, we have P5, so we have 3, 1. And then we also have 3, 5, 2, 4 to the other one. So here in this case, when we use an index to iterate over both, we will reach a point where the index for the first path can't increase, otherwise it's going to be an out of bounds. So that's an edge case that we need to check. So we're going to have a little while loop, I suppose, while true. We're going to start with an index 0. And we're going to increase our index every single time. So now let's deal with the edge case first. If idx is larger or equal than length path p, then we know the last element in path p is the result. Same thing for the path in q. If we've exceeded the length of the path of q, we know the last element on the path to q, this 5, was the result. Now, if we have not exceeded any of them, that's the regular case, right? So now we need to check if path p is unequal, at idx, of course, unequal path q at idx. What does that mean? That means that idx minus 1 was the lowest common ancestor. And yeah, and it's the same in both. That's what that means. That's exactly what that means. So yeah. And since it is guaranteed that P and Q are contained in our little tree here, we don't need any other terminating conditions, right? So it's guaranteed that either first the path P or path Q run out of length, or that we run into a node where they're not equal. And even if both nodes, let's say P and Q are 8, yeah, no, they have to be different even, right? Yeah, so it doesn't even matter, but yeah. I think that is everything we really need. I'm still thinking about what implementation I like better, but yeah, I think that is everything. I'm brave enough to now click the run button to see our test cases, if that works out, and boom, we get the wrong result. Now, why would that be? Let's look at this. So that's the first test. Which test case is it? The first one. Okay, so let's walk through the first example. So P is 5. So we should have in path to P, we should have 3 and 5, right? So this would be 3, 5. And the path to Q, 1, is 3 and 1. 3 and 1. Okay, we start at index 0 while true. If the index is larger than 2, which it isn't, it's also not larger than Q. And actually it's the same at the current index. Right? So this condition doesn't hold. And we pop out of it, because we're comparing 3 to 3. Now index is 1. We're still in the loop. We're not larger than 2. And now at index 1, we have 5 and 1, so they're different. Now I'm returning the path. Oh, it's -1 is of course wrong. It should be IDX minus wrong. All right, I overlooked that. So if we run this again, ta-da. Okay, that looks better. And yeah, let's also submit it to run it to all of the test cases that LeetCode has for it. And yeah, and luckily that works out just nicely. So I would say, so for this problem, the key is really to break it down into 2 parts, finding the paths to the nodes, and then just comparing the paths, the 2 paths. And if you want to do this at the same time, I think it's gonna be kind of difficult. You know, I think it's getting too messy if you do that. You know, you could imagine that maybe you do just a search, and you search for 2 nodes at the same time, and then you remember when you found one, and you continue your descent in the tree, and then if you find the second, etc., etc. So I think that would be too complicated. But what you could also do is, yeah, here's another approach. So what you could do is, when you go on the path finding to the node, on your way back up, when you come out of the recursive call, you could label each node that lies along the path, right? And then you could compute, you know, on the second descent to find the node, and then on the return, you could find the first node that has already been labeled to belong to the path to P. So that would be a way of how you could do that in one go. But I like this a little better. I like segmenting a problem into multiple steps, which, yeah, hopefully gives some good scores on an interview, because you were able to, well, slice and dice the problem and formulate it as sub-problems and implement them or solve them independently of each other. So yeah, that concludes LeetCode 236.